Step into noon sun and your screen vanishes. 3 stack tricks push a modern OLED past 8,000 nits. Break time equals 0. 6 is / bright enough to read outside, where a comfy indoor screen sits near 100 nits. 80 times brighter on demand. Here's the real problem. Direct noon sunlight lands somewhere between 10,000 and 120,000 lux of light. A dim screen just gets swallowed. Washed out, unreadable. This is the hardest visibility problem in displays. Outside, the screen isn't competing with a lamp across the room. It's competing with the sun itself. So how does a sheet of glass outshout a star? We'll climb the brightness stack from a single pixel up to the peak brightness boost. Trick 1 lives inside the pixel. Start with how the screen makes light at all. In an older LCD, one big backlight shines from behind. The light fights through layers of filters and shutters to reach your eye. A lot of it is lost on the way. An OLED throws that out. Each tiny dot on the screen makes its own light. No backlight to punch through, no stack of filters eating the glow. The light goes straight out the front. That's what emissive means. Every pixel is its own little lamp. 2 things fall out of this. First, efficiency. Because nothing blocks the light, more of the power you spend actually reaches your eyes. Second, and this is the sneaky one, black. When a pixel needs to be black, it doesn't dim a filter. It switches fully off. Dead dark. So a bright pixel can sit right next to a truly black one. In glare, that contrast is what keeps text sharp instead of muddy. Think of it as the difference between one floodlight behind a fence versus a grid of bare bulbs. The bare bulbs waste nothing and can go fully dark one at a time. This front-emitting base is the foundation. It gives the panel a high-efficiency ceiling. Headroom the next 2 tricks stack right on top of. But an efficient pixel is still just sitting there glowing gently. How do you make it scream? Trick 2, drive the pixels harder. Here's where it gets physical. Each emitter is basically a lamp. And a lamp gets brighter when you push more electricity through it. Send more current, get more light. Simple until it isn't. Push every pixel to maximum at once. A full white screen at full drive and 2 things bite back. The panel heats up fast, and running an emitter that hard ages it. It dims a little permanently every time. So there's a hard cap on how bright the whole screen can go and hold. That sustained, full-screen ceiling usually lands somewhere around 1,000 to 1,600 nits. Not 8,000. The panel simply can't run flat out everywhere and survive. Say that number again because it matters. Full white all the time tops out near 1,000 to 1,600 nits. That's the honest all-day brightness. So how do engineers lift that ceiling? Materials. Newer emitter chemistry can take more current before it degrades. And there's a structural trick, tandem OLED. Instead of 1 light-emitting layer per pixel, you stack 2, wired so they light together. 2 layers sharing the load means each one works less hard for the same brightness. So you can push the pair further before either wears out, and it runs cooler doing it. That's real headroom. But raising the ceiling for the whole screen still can't get you to 8,000. The heat and aging math won't allow full screen 8,000 for anyone. Which forces the real question. What if you don't light the whole screen? Trick 3 is where the 8,000 actually happens. And it's a budgeting trick, not a brute force one. Here's the key idea. The panel has a fixed budget of power and heat it can spend safely at any instant. Light the whole screen and that budget spreads thin across millions of pixels. Everyone gets a little, but light only a tiny sliver, and the controller can dump the entire budget into that one small patch. Concentrate the whole allowance on a few pixels, and those pixels go nuclear. This runs on something called average picture level. How much of the screen is lit and how hard, averaged across the panel. When the average is low, a small bright window on a mostly dark screen, the controller allows a huge spike there. So a bright patch covering just 1 to 3% of the display can hit 8,000 nits and beyond. Precisely because the other 97% is dark and the heat has room to escape. It's peak power aimed at a spotlight, not a floodlight. And the phone decides when to allow it. A light sensor watches the room. Auto brightness only unlocks this peak boost when it sees real sunlight. So indoors where you'd never need it, the panel is never stressed. Which tells you exactly how to read the box. That headline 8,000 nit number is a peak window figure. A small patch outdoors for a moment. It is not the brightness of a full white screen all day. Both numbers are real. They just answer different questions. Now watch the 3 snap together. The emissive base gives you front-emitting pixels that waste almost no light. That's your efficient foundation. Driving them harder with better materials and tandem stacking raises the ceiling of how bright each pixel can safely go. An average picture-level budgeting takes that raised ceiling and concentrates the whole power and heat allowance into a tiny window, which is how a sliver of the screen blows past 8,000 nits in the sun. Each layer needs the one beneath it. You can't run the peak window without the drive headroom, and you can't build that headroom without the efficient emissive pixel that wastes nothing to begin with. Pull out the bottom layer and the top collapses. Break time equals 0, 6 is slash, and here's what it means when you're actually buying a phone. Outdoor readability is a system trick, not one big lamp. So the two numbers on the box measure two different things. Sustained full-screen brightness is what you get all day, and peak window nits is that headline spike. Check both. They rarely match. So it was never one giant backlight. 3 stacked tricks, self-lit pixels, harder drive, and a concentrated peak boost. These are what carry a screen past 8,000 nits so you can read it in the sun. Next, how that light sensor and tone mapping actually decide the exact brightness moment to moment, and what running at peak costs you in burn-in over the years.